Hi. A programming language is a formal language comprising a set of instructions that produce various kinds of output. Programming languages are used in computer programming to implement algorithms. Most programming languages consist of instructions for computers. There are programmable machines that use a set of specific instructions rather than general programming languages. Programming languages are divided into three categories: machine language, low-level languages, also known as assembly language, and high-level languages. In this lecture, we will discuss about these types of languages one by one. Machine language. A computer programming language consisting of binary or hexadecimal instructions which a computer can respond to directly, sometimes referred to as machine code or object code. Machine language is a collection of binary digits or bits that the computer reads and interprets. Machine language is the only language a computer is capable of understanding. The exact machine language for a program or action can differ by operating system on the computer. The specific operating system will dictate how a compiler writes a program or action into machine language. Computer programs are written in one or more programming languages like C++, Java, or Visual Basic. A computer cannot directly understand the programming languages used to create computer programs, so the program code must be compiled. Once a program's code is compiled, the computer can understand it because the program's code is turned into machine language. Machine code is the only language a computer can process directly without a previous transformation. Currently, programmers almost never write programs directly in machine code because it requires attention to several details that a high-level language handles automatically. Furthermore, it requires memorizing or looking up numerical codes for every instruction and is extremely difficult to modify. True machine code is a stream of raw, usually binary data. A programmer coding in machine code normally codes instruction and data in a more readable form such as decimal, octal, or hexadecimal, which is translated to internal format by a program called a loader or toggled into the computer's memory from a front panel. Following example of machine language for the text "Hello World." Every character is converted into its binary form, and that's how it will be stored in the computer. Keep in mind that empty space will also be considered as a character. Although few programs are written in machine language, programmers often become adapted at reading it through working with core dumps and debugging from the front panel. A function in hexadecimal representation of 32-bit x86 machine code to calculate the nth Fibonacci number is given below. Low-level languages. A low-level language is a type of programming language that contains basic instructions recognized by a computer. Unlike high-level languages used by software developers, low-level code is often cryptic and not human-readable. Two common types of low-level programming languages are assembly language and machine language. Software programs and scripts are written in high-level languages like C#, Swift, and PHP. A software developer can create and edit source code in a high-level language using a programming IDE or even a basic text editor. However, the code is not recognized directly by the CPU. Instead, it must be compiled into a low-level language. Assembly language is one step closer to a high-level language than machine language. It includes commands such as move, add, sub. These commands perform basic operations such as moving values into memory registers and performing calculations. Assembly language can be converted to the machine language using an assembler. A low-level programming language is a programming language that provides little or no abstraction from a computer's instruction set architecture. Commands or functions in the language map closely to the processor instructions. Generally, this refers to either machine code or assembly language. The word low refers to the small or non-existing amount of abstraction between the language and machine language. Because of this, low-level languages are sometimes described as being close to the hardware. Programs written in low-level languages tend to be relatively non-portable. Low-level languages can be converted to machine code without a compiler or interpreter. Second-generation programming languages use a simpler processor called an assembler, and the resulting code runs directly on the processor. A program written in a low-level language can be made to run very quickly with a small memory footprint. An equivalent program in a high-level language can be less efficient and use more memory. Low-level languages are simple but considered difficult to use due to numerous technical details that programmers must be remembered. By comparison, a high-level programming language isolates execution semantics of a computer architecture from the specification of the program, which simplifies the development. Assembly language, sometimes referred to as assembly or ASM. An assembly language is a low-level programming language. Programs written in assembly languages are compiled by an assembler. Every assembler has its own assembly language, which is designed for one specific computer architecture. Why is ASM useful? Machine language is a series of numbers which is not easy for humans to read. Using ASM, programmers can write human-readable programs that correspond almost exactly to machine language. The disadvantage is that everything the computer does must be described explicitly in precise detail. The advantage is that the programmer has maximum control over what the computer is doing. Why is ASM a low-level language? Assembly is called a low-level programming language because there's nearly a one-to-one relationship between what it tells the computer to do and what the computer does. In general, one line of an assembly program contains a maximum of one instruction for the computer. How is ASM different from a high-level language? High-level languages provide abstraction of low-level operations which allow the programmers to focus more on describing what they want to do and less on how it should be done. Programming this way is more convenient and makes programs easier to read at the sacrifice of low-level control. Programs written in high-level languages will never match the raw speed and efficiency of programs written in assembly. Examples of high-level languages include Python, Java, JavaScript, and Lisp. What is a mid-level language? Mid-level languages provide some high-level abstractions to make the programmer's life easier, while still providing access to low-level operations. They are often used to write operating systems, so they are sometimes called system programming languages. Programs written in mid-level languages can perform as well or nearly as well as programs written in assembly language. Examples of mid-level programming languages include C, Ada, NIM, and Rust. Is ASM portable? The answer is no, because assembly languages are tied to one specific computer architecture. They are not portable. A program written in one assembly language would need to be completely rewritten for it to run on another type of machine. Portability is one of the main advantages of higher level languages. The C programming language is often called portable assembly language because C compilers exist for nearly every modern system architecture. A program written in C may require some changes before it will compile on another computer, but the core language is portable. Generally speaking, the higher level language is the fewer changes need to be made for it to run on another architecture. The lowest level languages, machine language and assembly language, are not portable. Example Hello World in 32-bit assembly for Windows. Here is Hello World written for 32-bit Intel processor. It will also run on 64-bit processor. We will compile and run it on Windows 10. To begin, open Notepad. Copy and paste the code above into a new text file and save the file as hello.asm. To compile the assembly, we use NASM, the Net Wide Assembler. It can be downloaded at the NASM site. NASM-F Win32 hello.asm. When you run this command, NASM creates an object file. An object file contains machine code, but is not quite an executable file. Our object file is called hello.obj. To create the executable, we use the 32-bit version of MinGW, minimum GNU, for Windows, which provides the GCC compiler. It can be downloaded at MinGW site. And then execute the command gcc-o hello.exe hello.obj. Let's discuss few terminologies. A microassembler includes a micro-instruction facility so that assembly language text can be represented by a name, and the name can be used to insert the expanded text into other code. A cross-assembler is an assembler that is run on a computer or operating system of a different type from the system on which the resulting code is to run. Cross-assembling facilitates the development of programs for systems that do not have the resources to support the software development, such as an embedded system or a microcontroller. In such a case, the resulting object code must be transferred to the target system via read-only memory. A programmer or a data link using either an exact bit-by-bit copy of the object code or text-based representation of that code, such as Intel Hex or Motorola S-Record. A high-level assembler is a program that provides language abstraction more often associated with high-level languages, such as advanced control structures and high-level abstract data types, including structures, records, unions, classes, and sets. A microassembler is a program that helps to prepare a microprogram called firmware to control the low-level operations of a computer. Meta-assembler is a term used in some circles for a program that accepts the syntactic and semantic description of an assembly language and generates an assembler for that language. Assembly time is the computational step where an assembler is run. Assembler. An assembler program creates object code by translating combinations of mnemonics and syntax for operations and addressing modes into their numerical equivalents. Their representation typically includes an operation code, as well as other control bits and data. The assembler also calculates constant expressions and resolves symbolic names for memory locations and other identities. The use of symbolic references is a key feature of assemblers, saving tedious calculations and manual address updates after program modifications. Most assemblers also include macro facilities for performing textual substitution, such as to generate common short sequences of instructions as inline instead of called subroutines. Some assemblers may also be able to perform some simple types of instruction set specification optimization. One concrete example of this may be the present x86 assemblers from various vendors. Called jump sizing. Most of them are able to perform jump instruction replacements in any number of passes. On request, Others may even do simple rearrangement or insertion of instructions, such as some assemblers for RISC architecture that can help optimize a sensible instruction scheduling to exploit the CPU pipeline as efficiently as possible. There may be several assemblers with different syntax for a particular CPU or instruction set architecture. Despite different appearances, different syntactic forms generally generate the same numeric machine code. A single assembler may also have different modes in order to support variations in syntactic forms as well as their exact semantic interpretations, such as FASM syntax, TASM syntax, ideal mode, etc. In the special case of x86 assembly programming. Number of passes. There are two types of assemblers based on how many passes through the source are needed. How many times the assembler reads the source to produce the object file. One pass assemblers go through the source code once. Multi-pass assemblers create a table with all symbols and their values in the first pass, then use the table in later passes to generate code. In both cases, the assembler must be able to determine the size of each instruction on the initial passes in order to calculate the addresses of subsequent symbols. The original reason for the use of one-pass assemblers was speed of assembly. Often a second pass would require rewinding and rereading the program source on tape or rereading a deck of cards or punched paper tape. Later computers with much larger memories had the space to perform all necessary processing without such rereading. Example: in the following code snippet, a one-pass assembler would be able to determine the address of backward reference BKWD when assembling statement S2, but would not be able to determine the address of forward reference FWD when assembling the branch statement S1. Indeed, FWD may be undefined. A two-pass assemblers would be determine both addresses in pass 1, so they would be known when generating code in pass 2. High-level assemblers. More sophisticated high-level assemblers provide language abstractions such as high-level procedures, functions, declarations, and invocations. Advanced control structures such as if-else switches. High-level abstract data types including structures, records, unions, classes, and sets. Sophisticated macro processing. Object-oriented programming features such as classes, objects, abstraction, polymorphism, and inheritance. Advantages of low-level languages. Low-level languages can make use of special hardware or special machine-dependent instructions. Translated program requires less memory. We can write code that can be executed faster. We have total control over the code. We can work directly on a memory location. High-level programming languages. In computer science, a high-level programming language is a programming language with strong abstraction from the details of the computer. In contrast to low-level programming languages, it may use natural language elements, be easier to use, or may automate significant areas of computing system, making the process of developing a program simpler and more understandable than when using a lower-level language. The amount of abstraction provided defines how high-level a programming language is. The first significantly widespread high-level language was Fortran. High-level language refers to the higher level of abstraction from machine language. Rather than dealing with registers, memory addresses, and call stacks, high-level languages deal with variables, arrays, objects, complex arithmetic or Boolean expressions, subroutines and functions, loops, threads, locks, and other abstract computer science concepts, with a focus on usability over optimal program efficiency. Unlike low-level assembly language, high-level languages have few, if any, language elements that translate directly into a machine's native opcodes. Other features, such as string handling routines, object-oriented language features, and file input-output, may also be present. One thing to be noted about high-level programming languages is that these languages allow the programmers to be separated from the machine. That is, unlike low-level languages like assembly or machine language, high-level programming can amplify the programmer's instruction and trigger a lot of data movement in the background without their knowledge. The responsibility and power of executing instructions have been handed over to the machine from the programmer. High-level languages intend to provide features with standardized common tasks, permit rich debugging, and maintain architecture, while low-level languages often produce more efficient code through optimization for a specific system architecture. Abstraction penalty is the cost that high-level programming techniques pay for being unable to optimize performance or use certain hardware because they don't take advantage of certain low-level architecture resources. High-level programming exhibits features like more generic data structures and operations, runtime interpretation, and intermediate code file, which often result in execution of far more operations than necessary. Higher memory consumption and larger binary program size. For this reason, code which needs to run particularly quickly and efficiently may require the use of a lower level language, even if a higher level language would make the code easier. In many cases, critical portions of a program, mostly in a high level language, can be hand coded in assembly language, leading to a much faster, more efficient, or simply reliable functioning optimized program. Execution modes. There are three general modes of execution for modern high-level languages: interpreted, compiled, source-to-source translated, or transcompiled. First, we will discuss about the interpreted. When code written in a language is interpreted, its syntax is read and then executed directly with no compilation stage. A program called an interpreter reads each program statement following the program flow, then decides what to do and does it. A hybrid of an interpreter and a compiler will compile the statement into machine code and execute that. The machine code is then discarded to be interpreted anew if the line is executed again. Interpreters are commonly the simplest implementation of the behavior of a language, compared to the other two variants discussed in this part of the lecture. Compiled mode. When code written in a language is compiled, its syntax is transformed into an executable form before running. There are two types of compilation. First one is machine code generation and second is intermediate representation. Machine code generation. Some compilers compile source code directly into machine code. This is the original mode of compilation, and languages that are directly or completely transformed to machine native code in this way may be called truly compiled languages. Intermediate representation. When code written in a language is compiled to an intermediate representation, that representation can be optimized or saved for later execution without the need to reread of the source file. When the intermediate representation is saved, it may be in a form such as bytecode. The intermediate representation must then be interpreted or further compiled to execute it. Virtual machines that execute bytecode directly or transform it further into machine code have blurred the once clear distinction between intermediate representations and truly compiled languages. Source-to-source translated or transcompiled. Code written in a language may be translated in terms of a lower level language for which native code compilers are already common. JavaScript and the language C are common targets for such translators. See CoffeeScript, ChickenScheme, and Apfel as examples. Especially the generated C and C++ code can be seen in the fgens directory of any compiled FL project. In FL, the translated process is referred to as transcompiling or transcompiled, and FL compiler as a transcompiler or source-to-source compiler. Note that languages are not strictly interpreted languages or compiled languages. Rather, implementation of language behavior use interpreting or compiling. Example of high-level language. The following code is written in C++ language. In this program, the preprocessing directive and using directives are used. This is the initial and necessary part of any C++ program. After that, main function is used with no return value. In the body of main function, one statement is written. This statement will display the line on the output screen which will be, every age has a language of its own. It is notable that in C++ every program statement ends with the semicolon and body of the function start and end with the parentheses. Examples of high-level languages include C++, Java, Pascal, Python, Visual Basic. Advantages of high-level languages. High-level languages are easier to modify as it uses English-like statements. It's easier to write code as it uses English-like statements. Easier to debug during development. Portable code. It's not designed to run on just one kind of machine. Difference between high-level and low-level languages. Both high-level languages and low-level languages are programmable languages. The main difference between high-level and low-level languages is that programmers can easily understand or interpret or compile the high-level language in comparison of machine. On the other hand, machine can easily understand the low-level languages in comparison of human being. Examples of high-level languages are C++, Java, Python, etc. Let's see the difference between high-level and low-level languages. High-level languages are programmer-friendly language. High-level language is less memory efficient. It is easy to understand. It is simple to debug. It is simple to maintain. On the other hand, low-level language it is machine-friendly language. Low-level languages are highly memory efficient. It is tough to understand. It is complex to debug comparatively. It is complex to maintain. Let's see some more differences. High-level languages are portable. It can run on any platform. It needs compiler or interpreter for translation. On the other hand, low-level languages are non-portable. It is machine dependent. It needs assembler for translation.